Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. Today I would like to talk on high pass filter from linear and digital integrated circuits. These are the topics which I want to discuss in this video. How the first order high pass filter will be designed with unity gain, and how the first order high pass filter will be designed with a variable gain, and how second order active filter is designed with unity gain, and last second order active filter with variable gain. First order high pass filter with unity gain. Input voltage has been given to a non-inverting terminal of an op-amp, and the feedback has been given to a inverting terminal of an op-amp, and a parallel combination of capacitor with resistor has been connected to a non-inverting terminal of an op-amp. This is exactly replica to the low pass filter. For low pass filter, input will be connected to a resistor and then connected to a parallel capacitor, and this input voltage has been given to a positive terminal of an op-amp. This placement of this resistor and capacitor will be exact replica for low pass and high pass filter. High pass filter is a complement of low pass filter. Hence, high pass filter can be obtained by simply interchanging R and C in the circuit of low pass configuration. The first order active high pass filter with unity gain is shown here in the figure, which is also called as a voltage follower. Now, to find out the transfer function for this circuit, we need to determine output voltage in terms of input voltage. That is, transfer function is given as ratio of output voltage to the input voltage. So, in order to determine the output voltage in terms of input voltage, just I will apply a voltage divide rule over here, and I can write this as R by R minus J XC into V in is the voltage across this point. This is the actual input to the operational amplifier. So, as your input voltage has been connected to a positive terminal of an op-amp, this circuit is going to be working as a non-inverting terminal op-amp. So, as you have not connected with any resistors over the feedback network, the output voltage is given as V0 is proportional to V in, and you can write this V0 by V in as R by R plus 1 by SC. And if you can solve this, if you can take R common in the denominator and numerator, you can write it as 1 by 1 plus 1 by SRC. As I am substituting S is equals to j omega, the transfer function H of S can be rewritten as H of j omega is equals to 1 by 1 plus, you can write this as H of j omega is equals to 1 by 1 plus 1 by j omega RC. Let us assume omega L is equals to 1 by RC. So, you can write this H of j omega is equals to 1 by 1 plus j into omega L by omega. So, this is how you can get H of j omega. The transfer function is equals to 1 by 1 plus j into omega L by omega, where omega L is equals to 1 by RC. The magnitude of transfer function can be given as 1 by root over omega L by omega whole square. Or if you want to write in terms of frequency, you can write this as H of j f is equals to 1 by root over FL by f whole square, where FL is the lowest cutoff frequency. So, here when f is equals to FL, H of j omega, the transfer function H of j omega will be equals to, or H of jf will be equals to 1 by root 2, which you will be getting it as a 0.707 value. That is, you will be having a 3 dB gain across this f is equals to FL. When f is less than f, you will be having a approximately 0 at the starting point, and it linearly increases to a cutoff frequency. and when your cutoff frequency is greater than FL, when your frequency of your signal is greater than FL, it start passing through the circuit. So, from 0 to FL, that is lowest frequencies band is called as a stop band, and above the cutoff frequency is called as a pass band. In high pass filter, only high frequency signals are going to be passing through the circuit and low frequencies are going to be rejected passing through the circuit. That is, the frequency band from 0 to lowest cutoff frequency will not be allowed to the circuit, and from above FL will be passed through the circuit. Next, this circuit shows the first order high pass filter with the variable gain. The difference between the unity gain and variable gain, as the gain for a non-inverting terminal is given as 1 plus Rf by R1. For unity gain, this should be equals to 1. So, we are not considering Rf and R1, and we are making the circuit work as a voltage follower. For variable gain, the gain is going to be changing with respect to Rf and R1 values. The active high pass filter with a single RC network connected to a non-inverting terminal of an op amp is shown here, and the input resistance Ri and the feedback resistance Rf are used to determine the gain of a filter in a pass band. And at low frequency, the capacity appears as an open circuit, so the voltage gain approaches to 0. So, the voltage gain approaches to 0. At low frequencies, capacitor appears as an open circuit, so the output voltage gain approaches to 0. And at high frequencies, the capacitor appears as a short circuit and the circuit becomes as a non-inverting amplifier with a voltage gain of 1 plus Rf by R1. The output voltage here, see, V1 can be given as V1 is equals to Vi into R by R minus jXc. As you have a input voltage, input resistance and feedback resistance, the gain of an non-inverting amplifier is written as 1 plus Rf by R1, can be given as V0 is equals to 1 plus Rf by R1 into Vin, where Vin is equals to Vi into R by R minus jXc, where minus jXc can be rewritten as j 2 pi fc. 1 by minus jXc can be given as j 2 pi fc. So, now this equation, if you can rewrite this expression, you can write this as V0 is equals to 1 plus Rf by R1 into Vi, and I am dividing with minus jXc in the numerator and denominator part. I can write this as R by minus jXc divided by R by minus jXc, plus 1. So, if you can substitute 1 by minus jXc with j 2 pi fc, again this equation you can write it as V0 is equals to 1 plus Rf by R1 into Vi into R into 1 by minus jXc can be given as j 2 pi fc divided by R into j 2 pi fc plus 1. So, you got this expression. The output voltage of a first order active high pass filter is given as V0 is equals to 1 plus Rf by R1 into j 2 pi f Rc divided by 1 plus j 2 pi f Rc into the input voltage Vi. So, if you can solve by assuming the cutoff frequency FL as 1 by 2 pi Rc, this equation you can rewrite this as V0 is equals to this 1 plus Rf by R1 is a gain of an amplifier. So, V0 is equals to A into J of F divided by FL, where FL is equals to 1 by 2 pi RC divided by 1 plus J F by FL. Vin, you got it as a denominator. This ratio of V0 by Vin, gain. The gain can be given as V0 by Vin, which you can write as A into J F by FL divided by 1 plus J F by FL. So, the frequency response of a filter is obtained from the magnitude of the filter. So, now magnitude of V0 by Vn can be given as A into F by Fl divided by root over 1 plus F by Fl whole square, which you can also write it as A divided by root over 1 plus Fl by F whole square. So, the magnitude or frequency response can be determined with the equation as H of F is equals to A by root over 1 plus Fl by F whole square, where Fl is the lowest cutoff frequency. That is, till that lowest cutoff frequency, the frequencies are not going to be allowing to the circuit. When it is just above the Fl, the frequencies are going to be allowing to pass through the circuit. The same has been explained here with a step by step. At low frequencies, that is when F is greater than Fl, at low frequencies, that is when F is less than Fl, the gain is approximately equals to A, and at frequencies F is equals to Fl, the gain falls to 0.707 times the maximum gain A, and the range of frequencies above Fl is called as a pass band, and at F greater than Fl, the gain decreases constantly of minus 20 dB. The frequency range below the cutoff frequency is called as a stop band, and the frequency range above the cutoff frequency is called as a pass band. It is from this circuit, from this point, we can say that high pass second order filter can be obtained from a low pass filter with a transformation of S of omega naught is S divided by omega naught as low pass filter is equals to omega naught by S at a high pass filter. Hence, the resistor and capacitor are interchanged in low pass filter to get a high pass filter. And these are the steps involved to design a high pass filter. First, we need to choose what is the lowest cutoff frequency, and then you need to choose a capacitor, whatever the capacitor value which is available to us, and substitute, and you can find the cutoff frequency by substituting. You can find out the resistor value if you know the cutoff frequency and the capacitor value, and simply you can design a circuit by knowing a R, C and FL values. And the gain of a filter is given as 1 plus RF by R1 into input voltage, and this is the gain for a non-inverting amplifier. Now, coming to a second order active filter with a unity gain. This is a basic circuit which can be used for both low pass filter and high pass filter, and this derivation has been given in the previous video, which is when I am dealing with the low pass filter circuit, and by applying a KCL over this node and over this node, and by solving you will be getting a transfer function of this generalized second order filter as y1 y2 divided by y1 y2 plus y4 into y1 plus y2 plus y3. This expression, the derivation for this expression has been given in the previous video when I am dealing with the low pass filter, and this directly I am using here to design a second order filter for a second order high pass filter. Now, the second order high pass filter is also called as a Butterworth filter, which is shown over here. The analysis can be done exactly the same way as for the low pass, except the derivation is set to 0 at S is equals to j omega is equals to infinity, and here the lowest cutoff frequency is assumed as a 1 by 2 pi RC, and the transfer function has been given as a 1 by root over FL by F whole to the power of 4. Generalized second order active filter with a variable gain. Here the op amp is connected in a non-inverting terminal. The result thus obtained can be analyzed from a low pass and high pass filter, and we can write directly the equation V0 is equals to 1 plus RF by Rn into Vb, where Vb is the voltage across this point, and you can write V0 is equals to AVB, where A is equals to 1 plus RF by R1. Now, this is a second order active filter with a variable gain, and here this transfer function have been derived in the last equation. Just I am using the same expression over here by placing y1 y2. See here I am using the same expression here to derive the second order active filter with a variable gain. Here for low pass filter I used to take y1 is equals to y2 is equals to r, and y3 y4 is equals to 1 by SC. Here This is represented with y1 and this is represented with y2 and this is represented with y3 and y4. Simply by interchanging y1 and y2, that is capacitors with the resistors and resistors with the capacitors, the second order high pass filter can be designed. Now, just by substituting this y1 and y2 as SC and y3 and y4 as 1 by R, you can determine the transfer function. This is a generalized transfer function for a second order filter. Either may be a high pass filter or may be a low pass filter. I have taken, instead of taking a resistor and capacitor value, just I have considered y1, y2 and y3, y4 to determine the generalized transfer function. This transfer function can be used to design a second order low pass filter as well as a second order high pass filter. That is the reason why I use the same equation over here also. The derivation of this h of s has given over here, or it has been explained in the previous video when I have dealt with the low pass filter. Once check that. And now here just I am simply substituting y1, y2 as SC and y3, y4 as 1 by R. And if you can solve this expression, you will be getting a final transfer function as h of s is equals to a into s square c square divided by s square c square plus 1 by R into 2 sc plus 1 by R plus sc by R into 1 minus a. So, if you can expand this expression, you can write a s square. So, it has been divided, at the same time it has been divided with c square on the numerator and denominator part, and you can write this expression as a s square divided by s square plus 2 s r c plus 1 by r square c square plus s by r c into 1 minus a. So, now again this equation has been written as a by s square plus 1 by r c if you can take common, 1 by r c if you can take common, you can get it as a 3, 2 plus 1, 3 minus a into s plus 1 by r square c square. As I am assuming omega L is equals to 1 by RC, I am rewriting this expression as AS square divided by S square plus 3 minus A into 1 by RC has been given with omega L into S plus omega L square. Now, if you can take S square common from numerator side, or you can say that if you have divided and multiplied with the S square, if you can divide with S square on numerator and denominator, the transfer function can be given as a by 1 plus omega L by s into 3 minus a plus omega L by s whole square. When s is equals to 0, h of 0 is equals to 0. When s is equals to infinity, h of infinity will be equals to a. It is observed that this configuration is for high pass filter. Therefore, the lowest cutoff frequency is given with 1 by 2 pi RC. And the transfer function has been derived. If you can substitute s is equals to j omega in the above transfer function, that is h of s is equals to a by 1 plus omega L by s into 3 minus j plus omega L by s whole square, and by assuming 3 minus j is alpha, and now the transfer function, if you can rewrite this expression, you can write as h of j omega is equals to a by root over 1 plus omega L by omega whole to the power of 4. In terms of frequency, you can write as a by root over 1 plus fl by f whole to the power of 4. This you can also write as 2n. This n represents the number of your order. If this is a second order, as we are deriving a generalized second order active filter, n will be given with the 2. So, it has been given as, transfer function as given as a by root over 1 plus fl by f whole to the power of 4. If it is an nth order, the transfer function has been given as a by root over 1 plus fl by f whole to the power of 2n. So, generalized nth order high pass Butterworth filter has been given with the equation as 1 plus 1 by root over 1 plus omega L by omega whole to the power of 2n. This n represents the nth order. For unity gain, h of j omega is given as 1 by root over 1 plus omega L by omega whole to the power of 2n. With unity gain, we will not consider the gain, but for variable gain, you need to consider the gain, because the feedback has been connected with the resistor, input resistor, and also a feedback resistor. In this video, we have we learned how to design a high pass filter with a unity gain and high pass filter with a variable gain. The difference between the high pass filter and low pass filter designing is interchanging of resistor and capacitor. And we also learned how to design a second order high pass filter. Here, to design a second order high pass filter, I use the derivation of transfer function of low pass filter, generalized transfer function of low pass filter, and in that generalized expression, I have substituted y1, y2 values as SC and y3, y4 values with 1 by R, and I have derived the transfer function for a second order high pass filter. The same generalized expression in terms of y1, y2 can be used for low pass filter as well as high pass filter. Thank you.